Happy Monday. Sorry about the live transcript. It's not working. All right, so just a couple of things, right? So you've got your first presentation. So the first presentation is due Wednesday, I want to say. Wednesday, November 10th. Yep, because then there's no classes on the Thursday or the Friday, right? I don't know, we don't usually have the Friday off, but that's new this year. I think they decided to do kind of a midterm break. November 10th at 23:59. Okay, quiz number 3 will be available after class on Wednesday until Sunday at 11:59. Okay, and it's of course a 50-minute timed quiz. And 20-ish questions. Okay, just like all the other ones, and it's really just testing material, theory material from class. Okay, what else? So there's that one, and then of course no classes on Thursday and Friday, right? So that means we don't have a class on Friday. So just remember that, right? Party time. Probably more like study time, but still. All right. So let's see here. For a little bit of review. All right. We talked about regression, and we talked about the least squares regression line, right? And so we talked about regression and the least squares regression line. In the least squares regression line, it minimizes the sums of the residuals squared. Now the residual, remember, is the distance from each point on your scatter plot to the line. So it's kind of weird. It's kind of this loop where the line adjusts until the residuals have all been minimized, right? Or the sums of the squared. That's the least squares regression line part. And so minimizes the sum of the residuals squared, right? And we talked about with one independent variable, then we are able to predict future values of y given some value of x. And that is the least squares regression line, right? And so the least squares regression line was y hat equals b naught plus b1x. And this is what we call simple linear regression, because there's only one independent variable. Right, so only one x. And the goal of making regression equations is to model the relationship, right? And so the model portion is this straight line, okay? And so this is the straight line model. of the relationship between X and Y. And the reason we do it is because Y hat is the predicted value of Y, right? So we do it so that we can predict future values of Y. Predicted value of Y. Okay, good. So we're gonna keep talking a little bit about the simple regression, simple linear regression case, and then we're gonna extend it to the multiple linear regression case, but that's really just introducing more than one X variable. So now you're gonna have X1, X2, X3, X4, blah, 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 up to, I mean, technically an infinite number of X's, but that'll never happen. So it'll be some number of X's, right? And so we'll talk about that. And really the idea stays the same, except now we have more independent variables incorporated into our prediction. Okay, so it kind of, it tends to yield better predictions. It can't yield worse predictions, but it might not be significantly better. So that's what we'll look at. In terms of B naught and B1, B naught is the y-intercept. And maybe I'll put it in brackets here. So it's the y-intercept, right? Thinking back to y equals mx plus b, right? Then of course the term that's not attached to the x is the y-intercept, and it is the predicted value of y when x is 0. Okay. While b1 is the slope, and the definition of the slope is that for each unit increase in x, we see a slope increase in the predicted value of y. So for each unit increase in x, we expect to see a slope increase. And we talked about, we can have negative slopes, of course, but it's just easier if we talk about slope increase. And then if the slope is negative, then that's fine. We expect to see a slope increase in the predicted value of y. Okay. What's nice about these definitions will apply in the multiple linear regression case as well, right? And so maybe I'll say these definitions will extend to the multiple linear regression case. Which just says that we have multiple independent variables. Multiple independent variables. Okay, so that's a recap from last day. Okay. So there are a couple of things, just kind of theoretical things that we usually need to touch on. They make pretty good theory questions on a quiz, so why not? But let's see here. So you might remember, or you might have seen these sums of squares. So the sums of squares for the residuals, for the regression line, for the total, for the errors, all that type of fun stuff. So here, let me just make this a little bit bigger here. And I also want to grab this graph. Copy. Wait. How about that? So we want our line to fit the data or to model the data well. And so what we do is we say that we're assessing the fit of the simple linear regression model, right? So does our model do a good job of modeling the data, right? And so here we have this example with some observations. I think we counted 10 observations last day. Right, and it's predicting the travel time based off of how many miles were traveled. Seems reasonable enough, right? And so here, right, we've got our least squares regression line, and we've got our observed values. And what we want to do is we want to have some sort of measurements that tell us how well does this line actually communicate the activity in the actual observed values, right? And so we talked about the residuals already, right? So that's one way that we could talk about it. Okay. The other way that we could talk about it is to look at the sums of squares due to error, which is basically looking at the residuals squared. Okay, and so we have your observed value. So each point is, of course, an observed value of y. And then the y hat is the predicted value of y. So it's the distance from a point, any point, maybe this one. So I have it off of the line, right? And so at that same value of x, we have some predicted value of y. Right. And so we could look at all those distances, and what we end up doing is we look at them squared and then we add those up. And those are what we call the sums of squares due to error. So we abbreviate it SSE for error. Okay. And so it's basically saying, right, what's the error once we use this line, right? What's the error from the observed values? We can also talk about the total sum of squares. Now, the total sum of squares looks pretty similar to the error sum of squares, except now we're looking at the distance from y bar. Okay, so of course, each observation has a value of y, and so we can calculate the average of that value. And so another measure of spread that we could consider is the typical measure of spread. How far away am I from the mean, right? And that's a classic measure of spread. And so we call that the SST, so for total. And so what that would look like is that maybe you have some y bar here, which would just be a straight line. So now you basically do the same thing, right? You see how far are all of these points, but not from the regression line, from the mean, right? We can do that. Okay. And so it's the same idea, but now we're thinking about how far from the y bar line are the points, and then the SSE is how far from the y hat line are these points. Okay. So then we want to talk about the sums of squares due to regression, which is different, because now I have a predicted value of y. So now I have some point on the regression line, so y hat, and then how far is that from the average, right? And so we've got all these differences that we want to look at and talk about. And so the SSR is the y hat minus y bar squared and then sum those all up. And what's cool, I guess, it's cool, but it's also pretty obvious, right? Maybe not right away, but if you spent some time, you'd see that the sums of squares of the total is the residual plus the errors, or sorry, I keep saying residual, it's not, it's the regression. So the total sums of squares is the distance that was from, sorry. The total sums of squares is the distance from the observed value to the average, right? So if you have that distance, SST, for this point here, okay, then this is the total, right, of the sums of squares. It's just one observation of that, right? But you can see now that that's the sum of how far it is from the predicted value and how far is the predicted value from the average, right? And so that's how the components are all made up. Okay. And so there's this relationship here. So if you have to find one of the three, right, you'll have the other two components and you can easily solve for those, right? And they're just going to be values. You've probably also seen an R squared value. If you're taking Stat 230 with me, we haven't seen R squareds yet, but R squared values are just kind of not technically, but often they're seen as just kind of how good of a relationship do I have here? How strong of a relationship and how strong is my model and how good is my model? So sometimes we'll use R squared or capital R squared. Okay. I guess technically, and I learned this from this textbook, the capital R is for multiple regression and a lowercase r is for simple regression. But honestly, most folks just use a capital R squared and don't distinguish between the two. So if you've taken stats before, right, we've calculated the correlation and then we square it. And so the correlation, which is also the correlation squared. Okay, so if you have the correlation, you can square it. But it also is related to the SSR over SST, making it a percentage, right? SSR as a percentage out of SST, right? And so if you think back, or if you haven't seen it before, then what the R squared is, and usually what I'll do is I'll say, oh, you have to memorize this definition. And as soon as you see percentage of variability explained by, so those kind of keywords, then your mind should go to R squared. Okay, and so the R squared can be interpreted as the percentage of the total sums of squares, right? Or if you see percentage of variability, it is R squared. Okay, so if you read the words percentage of variability, then it is R squared. So technically R squared is the percentage of variability in the y's that can be explained by the least squares regression line, right? That's a lot, right? But technically R squared is, don't need quotes anymore, the percentage, oops, the percentage of variability in Y explained by the least squares regression line on X. Okay. And that's what makes it a really common measure of how good your model is. Okay. And so this is what makes it a common measure of how good and I'm going to put in brackets here because it has to be a linear model. Okay. And so your linear model fits the data. Okay. I'm going to turn the light on. It's really dark in here. Well, it's not really dark. It's just kind of dark. It's getting darker. Oh yeah, daylight savings. Crazy. So often, you know, in reports and just if you're reading articles and stuff like that, they'll report the R squared and it should be pretty high. It's a percentage. And so you want a high percentage of variability to be captured by your regression line. And so here we want high R squared values. Okay. So we try to increase how much of that activity have we captured. So I think it was even on, oh, it's maybe from last day, but usually we put the R squared, maybe because we haven't introduced it yet, maybe it's not on here, but often we'll just include it in our regression output, right? Or somewhere in our report. And so in this example, where we're trying to predict the travel times, oh, I'm getting weird notifications here. Okay, backup in sync. I don't even use that anymore. It wants me to, it wants me back. Right, so we're looking at predicting the travel time based off of some number of miles traveled. Okay, for, I think it's a trucking company, if memory serves. So what we find is we can find that 66.41% of the variability in the values of travel time, that's your Y, right? In our sample, it can be explained by the linear relationship between the miles traveled and the travel time. That's the least squares regression line on X, right? And so they've just shown, so they've given those numbers, and we would just have R squared. A lot of our output is just going to give us R squared, so we don't need to worry about it so much. Okay. Usually if you're comparing models, the main way that we do that is using R squared values. And so if we are comparing models, we often compare the R squared values and pick the one with the highest R squared value. And pick the one with the highest R squared value. You can imagine that there are some things that go into that. So you can't just blindly pick the highest R squared value. You have to consider, especially in the multiple regression case, if you're including variables that are expensive to measure, for example, and it yields a minimal difference in R squared, well, that's not, you don't want to pick that one then. right? And so there has to be some thought that goes into it. You can't just blindly pick it. But if all the variables, I'm thinking maybe in a hospital case, right? If you're trying to predict some disease, maybe, right? Maybe it's not a great example, but it works, right? And so if we're trying to predict some disease and we have these kind of inexpensive tests and they're doing a good job of predicting that disease, then maybe our R-squared increased slightly by introducing this crazy, crazy expensive test. But you want to kind of think about, okay, can I implement this, right? Can I ask the hospital to bring in this crazy expensive machine for this small of a change in R-squared, right? So we always have to kind of step back and think a little bit and not just blindly pick the one with the highest R-squared. Although that's usually what I see when I'm doing consulting is people just go for the highest R-squared. They don't care. And often it doesn't matter. Okay? So if we talk about the multiple regression model, okay, and maybe what I'll do is I'll try to keep all of this together. I know there's a lot of text here, and I'm sorry about that, but I'll try to highlight the kind of key components here. So now we're going to talk about having two or more independent variables. So in general, what we have is we have some beta naught. So we still have some intercept, right? But now when we're kind of looking at x1 and x2, it gets a little messy, especially when we go up to xq, right? But the idea stays the same. It's hard for us to imagine, right? Q x's, I can't do it. But then, so we have some intercept, we have some slopes that are associated with each of the x's, and then we have some error term that that's just always going to be there, right? And so one thing that we're going to talk about is that the error term, which is oh, they've used two different epsilons, but anyways, it's a normally distributed random variable with a mean of 0 and a constant variance across all observations. So what does that mean? Well, it means that the error, which is the residuals, right? If we think back to our simple regression case, right? The residuals were the distances from the point to the predicted value. That's the same thing, except now we have multiple x's, so it gets hard to visualize. But we can still do the same thing and see how far was our predicted value from, or our observed value from the predicted value. And so once we have a look at all those residuals, then what we're going to find is that that we have this kind of even spread around the line. It's not a line anymore, it's a plane or worse. But basically this is like saying there's even spread around the line. I'll say line just to take us back to something that we can visualize. Okay. The interpretation of the y-intercept is similar to the interpretation in the simple regression. So we said the y-intercept is the predicted value of y when x is 0. Okay. Oh yeah, but now in the multiple regression model, we have more than one x. Sorry, I forgot to read the rest of it, right? And so now we have more than one x, and so now all of them have to be set to 0 because otherwise you don't have the predicted value of y, right? And so on the other hand, the slope coefficients are going to be a little bit different. Okay, it's still a change in the predicted value of y, but the key is that it's the change in the predicted value of y holding all the other variables and all the other values and slopes steady, right? So assuming that they're not changing, then we can interpret each of the slope coefficients. Okay, and so I'm going to highlight this maybe in pink. Oh, kind of dark there. How about lime green? There we go. Okay, so that's an important change, right? So this is where it differs in the multiple regression case, because in the simple regression case, we only had one value of x, and so it doesn't matter, right? But now I have multiple slopes, right, and multiple independent variables, and so now beta j, which is, well, just any one of these betas, right, some slope coefficient, represents the change in the mean value of y in the, oh, that's not the one I wanted to read to you. This one, the highlighted one, surprise, surprise. So beta j represents the change in the mean value of the dependent variable. So that's the expected predicted value of y, right? And so that's the same. That corresponds to a 1 unit increase in the independent variable xj. So that part is exactly the same as simple regression, holding all values, holding the values of all other independent variables in the model constant. So that's where it changes. Okay, and so that's important if we have to, you know, interpret some of these coefficients. Okay. So just as we did before, we have our theoretical model. So this is kind of this is our population model, but we don't know our population. And so that's, you know, tale as old as time. And so now we have this estimated multiple regression equation. And so now I have these B's that I'm going to estimate, right? So we use data to estimate these coefficients. And again, y hat is the predicted value of y. So just as before, right? So just like in the simple regression or a simple linear regression case, we were trying to minimize the sums of the residuals squared. And that's exactly what we're doing here, except now we have many different values, right? We have many different values of x, and so we'd have to look at all the different combinations of x. So what we're going to find is that we're going to focus, or actually, I don't want to highlight that quite yet. This is what I wanted to highlight, but let's focus on 2 independent variables, right? So just x1 and x2, because that we can visualize with a plane. Okay. And so here, let's focus on 2 independent variables. And so what we're going to find is that we have some y hat is some intercept plus beta 1 or b1 x1 plus b2 x2. So we have some coefficient on x1 and some coefficient on x2, and we can interpret those once we have some values. But for now, the SSE, so the sums of squares of the errors, the total, and the regression, you use the same calculations that we did for the simple linear regression case, right? And so that's interesting because we can have some average of y, right? We still only have one value of y, right? We just have multiple values of x. And so we still have observed values of y, we still have a mean of y, and we still have predicted values of y. But if we have two variables, and this is the one that we can kind of sort of wrap our heads around, is something like this. Okay. So if you have we're trying to predict the delivery time, and initially we only looked at the number of miles that the driver traveled, right? But now what if we incorporate another variable, the number of deliveries? So for each value of x that you incorporate, you're going to introduce another axis, and we really, you know, max out visually at 3. Right, but now we have some plane instead of a line, right? In the one variable case, or in the one independent variable case, we get a line and it's nice to look at. Here we have two variables, right? And so this is for two variables, two independent variables, two independent variables. And so now we have this plane, but that plane gives us a plane of predicted values. Plane of predicted values. Okay. There's a lot of math that goes into this, right? And so we're not going to go deep into that, but you know, it helps if we can kind of have this understanding of, okay, there's going to be some predicted value, and then we measure distances from that plane or from that line, so on. And so here we said that these are going to be calculated in the same way that we did before, which means that the coefficient of determination, which is the r squared, maybe I'll highlight that here. That's your r squared. Oops. And here they're saying in the multiple regression case, we're going to change the notation. I don't know if that makes sense. And then they start using r squared. I'm sure it's technically correct, but like I said, usually we just use r squared across the board. So remember, the r squared is the SSR over SST. So if they're calculated the same way that we did before, then nothing's changed. Then we can find the r squared, which is the SSR over SST again, right? So that's kind of cool. So we'll still be able to get some r squared, which is kind of a relief, right? Because we know that that's a pretty common measure of how good of a model do I have. So if we have some output, let me copy this. Consider regression output for two independent variables. This is from Excel, but honestly, it looks pretty similar in R. But save myself some time. Figured I would just use their output because then we can talk about it. And so typical output includes things like the multiple R, which it's just saying that you have a multiple regression. And so that's the correlation, the R squared, which is that value that we're looking at, right? We want a high R squared, and R squared of 81.7% is nice and high, so that's good. And so this is one of the main players that we're looking at here. We could also look at the adjusted R squared. That's going to be more important if we've introduced more variables. And so if you have a ton of variables, then you should be looking at the adjusted R squared, because you should be penalized for having too many variables in there, but we'll talk about that. We also have a standard error and the number of observations, but let's just kind of parking lot that for now. We're not really going to talk about the ANOVA, but the ANOVA, it basically is this kind of initial test, right? And so it develops the sums of squares for the regression, the sums of squares for the residuals, so that's SSE, and then it has the SST. So remember, we can calculate the R squared from that, right? And so a lot of it is developed as kind of a shortcut, okay? And what the ANOVA is doing is eventually it calculates a test statistic, and it's testing the hypothesis that there is, well, the null hypothesis is that all the slopes are the same. And there's nothing happening here. There is no way that any of these variables are going to help you predict your Y that you're trying to predict, right? Most often, you're going to have a small p-value here because there's often something going on. Okay. And so ANOVA is an analysis of variance. And it's basically a gatekeeper, right? And so it's basically a gatekeeper. Is there or does any English, do any of the independent variables help in predicting Y? Help in predicting Y. A significance F less than 0.05 means the answer is yes. Okay. It's technically, it's checking the null hypothesis that that mu, no, let's not go there. Can of worms. There. Phew. Let's not go there. Okay, but so this was more important back when we didn't have computing power, right? Or computing power is really, really expensive. Then you wanted to have a quick look, and there was this test that could tell you, hey, is there anything going on here? Is there anything worth looking into? Yes, there is. Okay, great. Then I'll spend my time and I'll actually do it, right? As opposed to if you're finding that, no, there's nothing going on here, that's going to save you a lot of time, right? And so for us now, it's more, you know, we include it because that's how it's always been done. But what we're really after is this portion here. Mostly. Okay, and so the intercept and the coefficients and their coefficients are the estimates. So the coefficients equal the slope estimates, slope or intercept estimates. So what we would have in our case, we're trying to, so in this case, we're trying to predict the average, the mean delivery time. So in this case, we would say that the delivery time, so Y is the delivery time. So then we would say the predicted delivery time, which I'll just throw a big hat on there, is going to be 0.1273, and you know what, let's just round it to 7. We'll round to 3 decimal places, looks good. Usually what I do is I look here and make sure that, because I want to be consistent, right? And so then I'm going to round to 3 decimal places, just make sure it captures enough activity on all 3 in this case. So the predicted delivery time, and let's move it over here, is the intercept plus 0.067 times the miles plus 0.690 times the deliveries. So in terms of how do we interpret this, well, the intercept is not interesting, right? Because we're not going to predict a delivery time when the miles is 0 and the deliveries is 0. So that's not, you know, it's not interesting. But we can talk about this intercept 0.067, or sorry, the slope 0.067. That's the predicted increase, or the expected increase in the predicted value of the delivery time for each additional mile, assuming that the number of deliveries is held steady, right? And then, so we can look at them individually, right? We can look at all the different combinations, but I've got them here. And I think I already talked about some of this here. So from this output here, right, from these coefficients, you can build out this model, right? And so this is your model. It's your least squares regression model. So we can interpret this as for a fixed number of deliveries, right? So holding deliveries steady, the expected, we estimate that the mean travel time will increase by 0.0672. I guess I should have gone to 4 decimal places to match. That's okay. Hours. Time is tricky, right? Because there's only 60 minutes, and so it gets confusing. But if you multiply it by 60, you get it to minutes. When the distance traveled increases by 1 mile. So it assumes that the number of deliveries is being held steady. And then same thing for a fixed distance traveled, so for a fixed number of miles, right, we estimate that the mean travel time will increase by 0.69, so about 41 minutes if you multiply it by 60, when the number of deliveries increases by 1 delivery. Okay. And so here we already talked about this, but the interpretation of the y-intercept, which in terms of this question is the expected mean travel time for a driving assignment with a distance traveled of 0 miles and no deliveries. That's not going to happen, right? So it's not meaningful because we're extrapolating, right? We never go 0 miles and we never have 0 deliveries if we're a delivery company, right? And so we talked about extrapolation before, right? What you can think of the intercept as just an anchor, right? And so we need somewhere to in the simple case, anchor the line, right, or anchor the plane, and you can force it to be 0, but it's going to change your predictions a little bit. Often the y-intercept is just an anchor for the line or for the model, I'll say. Because it's not necessarily a line. We've seen that it can be a plane. So we can find, and we'd use software for this, right? So we can find the r-squared, and it's here in the output. We have an r-squared of 81.73%, or yeah, to 4 decimal places, 0.8173. So that's our r-squared. And so the only thing that's different here is that we've added the number of deliveries, right, to the model. And so now it explains 81.73% of the variability in our sample, as opposed to in the simple linear regression case where it was only explaining 66.41%. So now we've explained an additional 15.32% of the variability in our sample values of travel time. So the addition of the number of deliveries to the model appears to have been worthwhile, right? So here's an example of, okay, this is how we compare models, right? And so this is how we compare models. We already said that, but it's worth saying again. Okay. So what we do is we can do inference for these slopes, right? Or for these point estimates of the betas, beta naught, beta 1, beta 2, beta 3, blah, blah, blah. And so what we can do is we can do hypothesis tests, but we can also do confidence intervals, right? And so what we need is to do a hypothesis test. We need the point estimate, and we need the standard error, and we need some null value, right? And so I'm going to show you briefly how we could do it, but also that it's already included in the regression output that you're going to look at, right? And so, but before we can do any inference on so the inference is going to be on the coefficients here, right? The coefficients are the point estimates of the slopes, right, of the betas. And you might have even seen it. It gives you the standard error of each of the coefficients. It also gives you the t statistic. It also gives you the p-value. So there's really no work that we have to do here. We just need to read these and understand what they mean, sort of. Okay, and so we can do hypothesis testing about the estimates, or we can do confidence intervals. But before we do that, how about just grab this whole chunk of change here? I know it's a lot of text. Can I extend this just a, could not. There. Okay, so we can do inference on these estimates, but we need to check some conditions first, okay? And so our inferences are valid only if the error term behaves in a certain way, okay? And so what we have to check is how well do the following two conditions on the error term, how well the following are met. I don't know, doesn't make sense. But anyways, it's the same condition always. So what we look at is, are these error terms normally distributed with a mean of 0 and constant variance, right? So basically, in the simple linear regression case, are the points randomly scattered around the line? You don't want to have some relationship around the line. You want to have random scatter around this straight line, right? And then the values of the residuals are statistically independent. So just because a previous observation was underpredicted, right, that doesn't mean that the next one has to be underpredicted. It can be, but it doesn't have to be because they're independent. Okay, and so really all we're looking for here is random scatter around around the least squares regression line. Oops. Okay. Oh, and I guess it says that here, right? And so that the regression estimates are unbiased, which means they don't tend to over or under predict, right? And so what we're going to look at is we're going to evaluate whether the error of an estimated regression equation reasonably meets the two conditions. And so the sample residuals we find by the observed value minus the predicted value. And so remember, the residuals, E subscript I is the residuals, or residual I, which is the observed minus the predicted value at I, which is the observed minus the predicted. Okay. So once you have your regression equation, it's usually very easy. You just ask for the residuals and they'll have been calculated and they'll just be given to you. Okay. And so there are lots of ways that we could run diagnostics on this, right? And so, but usually simple scatter charts of the residuals versus the predicted values of the dependent variables and the residuals versus the independent variables is usually enough for us to get a good understanding. Okay, and so what we're going to have is so the residuals are going to go on the y-axis, and the predicted values of y go on the x-axis. That's weird. Okay. And so what we're going to look for is the residuals should be scattered around 0. Okay. Look for random scatter around 0. So now you're not looking for a relationship, you're looking for this random scatter around 0. Okay, So that's the first one. And then, and the residuals versus the independent variables. So then you also look at the same thing. You look at against X1, the residuals, and then do the same thing up to XK, which can get really annoying, but you're looking for the same thing. So you look for random scatter around 0. So again, you have this line at 0 typically, and you want to look for random scatter around 0. Okay. Once you've confirmed that you're satisfied with how the residuals are behaving, right? So here I've got a fancier version of the same thing. Okay. So here you've got your y hat, you've got your residuals, and you've got this random scatter around 0. And so now it looks like the assumptions for inference about these coefficients, it appears the assumptions for inference about the coefficients are satisfied. So once you've checked that, then we can go ahead and we can look at those T statistics or just any inference in general. So what we're going to look at, let's go here. Oh, want to spread it out a little bit there. So that's when, so now that you've checked the assumptions, right? Are my residuals, are they normally distributed around 0? You could even make a histogram of the residuals and look at it that way. Do you have a normal distribution around 0? So once you're satisfied with that, then we can go ahead and we can test the regression parameters. So what we're saying is that, okay, if the coefficient is 0, then that X value is not doing anything in helping me predict values of Y, right? So here, we may wish to determine whether statistically significant relationships between the dependent variable Y and each of the independent variables X1, X2 up to XQ individually have some statistically significant relationship, right? And so note that if beta J is 0, then the dependent variable Y does not change when the independent variable Xj changes, right? Which is really saying that there's no linear relationship between Y and that variable Xj. If the coefficient is significantly different from 0, then we can say that there is a linear relationship there, right? And it is helping us predict values of Y. So beta J helps predict values of Y. Okay. So our null hypothesis is that beta j equals 0, and then our alternative hypothesis is that it's not 0, so it is contributing, and there is some relationship there. Now, in terms of the test statistic, you take the estimate or the coefficient from regression output, and then we want the standard error of that coefficient. Okay, and it gives us some t statistic. Now, we've seen just briefly that t is basically a normal distribution, except it depends on the degrees of freedom. And so we don't need to worry about how many degrees of freedom do I have, because it's always included in our regression output. Okay, and so here, so the point estimate and the standard error, or the standard deviation. So here, statistical software will generally report a p-value for this test statistic. So it is a t, and we could talk about the degrees of freedom, but it's always included, so we don't need to worry about that. So the key is, once you have a p-value, right, a p-value less than 0.05, typically, means that we can reject H naught. Means we have enough evidence to reject H naught, which in this case, if we're rejecting that this coefficient is basically 0, then we're saying, okay, no, there is some relationship here, right? And so therefore, if the p-value is small, the coefficient has a relationship with y, right? Or the x value has a relationship with y, right? And so it helps in predicting y. It helps in predicting y. Okay. And talks about that a little bit more, but let's go back and grab that output so we can see what's going on. Oh, and I think it's even, oh no, that's jumping ahead too much. Let's grab this again, copy, and I'll just do a smaller version of it. Gonna crop top. Okay. Here in this output, right, we have the standard error of the coefficient, we have the t statistics, and so we see that we have two very large t's, which means that we're out in the tails. So of course our p-values are going to be really, really, really small, and the only one, the p-value for the intercept, is 0.5353, so that's not small. The problem is, well, you have to have some anchor, right? And so the intercept is actually rarely significant, but we keep it in there because we have to have some anchor. Okay. And I'm sure I have that somewhere in here, so let me see. Just trying to see what I've copied in and what I haven't. Oh yeah, Okay, so that's good. So what we see is that, okay, these guys are both significant, which means that the miles and the deliveries both help towards predicting that value of y, the delivery time, right? And so what we're going to see is that the intercept is rarely significant, but we need an anchor, right? So, but we need an anchor. Okay. And so if all the x's are 0, then what's our predicted value, right? That's the definition of the intercept. Okay, so here, that's this chunk. So you can basically ignore the standard error in the t-statistic and basically just look at the p-value for each coefficient. And usually, you know, if they're contributing, then the p-value is going to be really, really small. Notice this is scientific notation, right? Times 10 to the negative 83. Imagine moving your decimal place 83 places. Oh no, no, thank you. We can build a confidence interval around the coefficient, right? So around the estimate, and that's going to help us determine, you know, is 0 inside this interval or not, right? And so again, the interval, so you can make a 95% confidence interval, or you can ask for a 99% confidence interval, or why not do both? Who knows? I usually just do the 95, gets me what I need, right? And so now if I look at the interval for miles and deliveries, I see that both of them are above 0. And so they're significantly different from 0, right? And so here, to test if beta j is 0, right, then you can build a confidence interval. And if the resulting confidence interval does not include 0, then we can conclude that beta j differs from 0 at that level of significance that you built the interval at. So the 95% confidence interval is my go-to. And so that's at the 5% significance level, which is that 0.05 that I mentioned earlier. Okay. What if I have non-significant independent variables? So what if I'm looking at this output, and what if the intercept wasn't the only one with a relatively large p-value, right? Then what do? There are a couple of scenarios, and just as we started talking about today, you have to use your judgment, and often you'll have to kind of rely on prior knowledge about the data that you're looking at. So sometimes you'll have a coefficient that's not significant, but you know, just from life or just from working with these with this data for so long, that it usually has a relationship, and so you just happen to not see a relationship right there. Then you should keep it in the model, right? And if you can be convinced to remove it, then there are different ways that we can remove non-significant independent variables. Okay. And so how do you handle the corresponding independent variable when there's an insignificant result? And so this is kind of vague, right? But it basically boils down to just what do you feel like doing? You're the analyst, so you get to make these decisions. Okay. And so there are many ways. There are many ways to remove non-significant, I don't want to say insignificant, non-significant variables. Non-significant independent variables from the model. Okay. Typically, what we do is we bump it down and make it the last independent variable. And then if it's still insignificant, then we can remove it. There's like a process there. But one thing is that even if you remove a non-significant independent variable, then it's possible that some of those variables that had significant coefficients, now those p-values might change, right? And so you might want to play around with it a bit before you decide on a model. And that's most of your job, right? Is playing around with the model and taking away variables, adding variables, seeing what's going on. And so that's something to keep in mind, is that if you remove even a non-significant variable, maybe it's carrying some of that weight, even though it's not significant, maybe it's carrying some weight or it's carrying some information. And then when you remove it, the other variables are left to carry the load, right? And then, so now maybe there's some information lost and they need some help, right? And so sometimes you'd have to include that non-significant variable just because otherwise the other variables are lost. There's some information there that's helping those variables be the best predictors that they can be. Okay. Hey, I'm all out of time. I'll leave it there then, I guess. But definitely read through the notes because it's on the quiz. So, eek, the quiz, right? If you have any questions, let me know. Otherwise, I'll see you guys on Wednesday. I'll stop this here.